Hello everyone. In this video, we will discuss the stability of cyclohexane molecules. By the end of this video, students would be able to assess the relative stabilities of cyclohexane molecules. Now, to approach a problem like this, start by drawing the molecule in its chair conformation. And ideally, you want to draw both possible chair conformations for the molecule. Now I've shown a cyclohexane molecule in its chair conformation on the upper right hand corner of this slide. Notice how each carbon, when a cyclohexane is drawn in its chair conformation, has two substituents. One of these is called the axial substituent, labeled by an A in this picture. The other substituent is called the equatorial substituent, and it's denoted by an E in this picture. Now, when a given carbon in this cyclohexane molecule is pointing up relative to its neighboring carbon atoms, then the axial substituent on that carbon points up and the equatorial substituent points down. Similarly, when a carbon in the cyclohexane is pointing down relative to its neighboring carbon atoms, then the axial substituent on that carbon points down while the equatorial substituent points up. Once you have the structure, then evaluate the number and size of the axial and equatorial substituents. Recollect that substituents are more favored in the equatorial positions. These positions are in some sense more roomy than the axial substituents. Axial substituents, when a molecule is drawn in its chair conformation, result in destabilizing 1,3 diaxial interactions. For example, if we look at one of these carbons, and let's say if we say this is carbon number 1, then we have carbon number 2, and that would be carbon number 3. And what 1,3 diaxial interaction means is that the two axial substituents on these carbon atoms can interact with each other and cause destabilizing steric interactions. Now, the same applies to any other set of carbon atoms. So if we start with carbon number 1 here, and let's say if this is 2 and this is 3, then the two axial substituents on these carbon atoms result in these destabilizing 1,3 diaxial interactions. Now, a more stable conformation is the one where most, if not all, of the substituents occupy equatorial positions. Now, when working with a molecule which has substituents with varying bulk, the more bulky substituent is favorable in an equatorial position. That would give us the more stable conformation. So now that we know some of the rules that we need to follow and the approach that we will use to assess the stability of these molecules, okay, let's go ahead and determine which of these two compounds is more stable. We have two cyclohexanes, each bearing two methyl groups. Notice how the two methyl groups are on carbons that are related to each other as 1 and 4. So these are in some sense 1,4 dimethyl cyclohexanes. And beyond the numbering itself, it is also a good idea to establish the stereochemical relationships between the two methyl groups. In the cyclohexane on the left, one of the methyl groups is on a wedge and the other methyl group is a dash, which means that these two methyl groups are related to each other as trans. Whereas on the cyclohexane on the right, both methyl groups are on dash bonds, which means the stereochemical relationship between these two methyl groups is of the cis kind. Now that we've assigned the numbering on the carbon atoms, as well as or assigned the positions to these methyl groups, as well as assigned the stereochemical relationship between them, let's go ahead and convert these cyclohexanes into chair conformations. And we will try to draw both chair conformations for these cyclohexanes. And also, when we are working with these conformations, it is okay to omit substituents on every other position, because we are only concerned with the methyl groups that are on carbon numbers 1 and 4. So if we assume that the headrest on this cyclohexane is carbon number 1, that would make the footrest on this cyclohexane carbon number 4. So to make the methyl groups trans to each other in this chair conformations, we are going to put one of the methyl groups on the axial position, and that means the other methyl group should also be in an axial position. This would make these trans to each other. Now we can go ahead and draw the other possible chair conformation. And now the headrest in the first chair conformation should become the footrest, and the footrest should become the headrest. And similarly, the methyl group which was on an axial position on carbon number 1 should now go equatorial. So the methyl group ends up on the equatorial position, and the methyl group which was also axial on the other carbon atom, which is carbon number 4, would also become equatorial. So the two methyl groups are now in equatorial positions. Now we can go ahead and similarly draw the chair conformations for the other cyclohexane. Now in this particular case, both methyl groups have a cis stereochemical relationship with each other. And that means if I put one of these methyl groups on the axial position on carbon number 1, then it should end up in the equatorial position on carbon number 4. So again, we are going to call the headrest carbon number 1 and the footrest carbon number 4. And I'm going to put the methyl group on an axial position on carbon number 1, and now I cannot put the other methyl group on the axial position because that would make it trans. So to make these cis, we're going to put the methyl group in an equatorial position. Now we will go ahead and complete this by drawing the other cyclohexane conformation that's possible for this molecule. And here again, the headrest now becomes the footrest, and the footrest becomes the headrest. And similarly, substituents that were axial in the other conformation would be equatorial in this new conformation, and any equatorial substituent would become axial in this new conformation. So now that we have both possible conformations for these cyclohexane molecules, let's focus on this cyclohexane on the left hand side, which is the trans dimethyl cyclohexane. Notice how in one of these conformations both methyl groups are axial, which means these would result in destabilizing 1,3 diaxial interactions. Now, in the other conformation, both methyl groups are equatorial, so this is stable. Now, when we go to the other cyclohexane, which is the cis 1,3-dimethyl cyclohexane, in each conformation, we have one methyl group that's axial and one methyl group that's equatorial. That means these overall have equal stability. But the molecule on the left, the trans-dimethyl cyclohexane, it is going to spend most of its time in the di-equatorial conformation. So this will be favored at equilibrium, and which means overall this is the more stable cyclohexane compared to the other one. So of the two cyclohexanes, the trans-dimethyl cyclohexane is more stable because it has at least one conformation where both substituents are in equatorial positions. So hopefully this was helpful in kind of identifying how we go through these cyclohexane molecules in assessing their relative stabilities. So we can basically look at the position of the substituents and the number of the substituents and predict which of the cyclohexane molecules is the more stable molecule. Thank you.